you for being here. Whether you found this channel yesterday or you've been here from the beginning, it means everything that you press play. Get comfortable. Let your body sink in to wherever you are. You don't need to hold on to anything tonight. Just let the words carry you. Tonight, we're going to talk about endings. Not the kind that bring grief, but the kind that make everything else possible. The death of stars. Part 1. Nothing lasts forever, not even the sun. Every star you have ever seen is dying. Not quickly, not in any time frame a human life could witness, but every star in the night sky is burning through a finite supply of fuel, hydrogen, fusing it into helium in a process that generates the light and heat that makes life possible, including our sun. Right now, the sun converts about 600 million tons of hydrogen into helium every single second. It has been doing this for 4.6 billion years, and it will continue for roughly another 5 billion years before the consequences become impossible to ignore. 5 billion years sounds like forever. It is not. On the scale of the universe, which is 13.8 billion years old, our sun is already middle-aged. It has lived more than a third of its total lifespan. The second half has already begun. And when the hydrogen in its core finally begins to run out, things will change in ways that are difficult to imagine from here. The sun will expand, slowly at first, then dramatically. As the core contracts and heats under its own gravity, the outer layers will push outward, swelling over millions of years into what astronomers call a red giant. The sun's diameter will eventually grow to somewhere between 100 and 200 times its current size. At that scale, it will likely engulf Mercury, then Venus, and possibly Earth. The oceans will have long since evaporated, the atmosphere long since stripped away, but the expansion itself, that slow, inexorable blooming of a dying star, will be one of the most dramatic events the solar system has ever witnessed. And it will happen, not as a possibility, as a certainty, written into the physics of the universe from the moment the sun ignited. Part 2. The Red Giant. A red giant is not a star in its final moments. It is a star in transformation. When the hydrogen in the core runs low, the core contracts under gravity and heats up. That heat ignites a shell of hydrogen surrounding the core, which burns more intensely than the core ever did. The extra energy pushes the outer layers of the star outward, and the star expands. Red giants are enormous. Nebula. Not every star dies in an explosion. Stars like our Sun, medium-sized, unremarkable, quietly burning, end their lives in a far gentler way. And paradoxically, one of the most visually stunning ways in the universe. As a sun-like star expands into a red giant, its outer layers become increasingly loosely bound. Over time, over thousands of years, those layers drift away from the core, slowly, like smoke rising from a candle that is almost burned out. That drifting shell of gas, illuminated by the dying star at its center, is called a planetary nebula. The name is misleading. It has nothing to do with planets. Early astronomers, looking through primitive telescopes, thought the round, glowing shapes resembled planets. The name stuck, but what they are is something far more profound. A planetary nebula is the last breath of a star. The Helix Nebula, roughly 650 light-years from Earth, is one of the closest planetary nebulae to us. It spans roughly 3 light-years across. From Earth, it appears as a ring of blue and red gas, glowing softly in the dark. At its center, a tiny, intensely hot remnant of the original star. It has been called the Eye of God. And looking at images of it, it is easy to understand why. The Ring Nebula in the constellation Lyra is another. A perfect ring of glowing gas, the expelled outer layers of a star that died roughly 4,000 years ago. At its center, the remaining core, now a white dwarf, is roughly the size of Earth, but contains more than half the mass of the original star. A star compressed into something the size of a planet. These nebulae don't last forever. Over tens of thousands of years, the gas disperses, the glow fades. The material drifts outward into interstellar space, eventually mixing with other gas and dust clouds. Some of it may eventually become part of a new solar system, new planets, perhaps new life. The last breath of a star becomes the raw material for everything that comes next. Part 4. The White Dwarf. At the center of every planetary nebula sits what remains of the star's core, a white dwarf. It is one of the strangest objects in the universe, a stellar remnant roughly the size of Earth, but containing the mass of a star. A teaspoon of white dwarf material would weigh roughly 5 tons on Earth. It produces no energy through fusion. It generates no new light of its own. What you see when you look at a white dwarf is not burning. It is cooling. The residual heat of billions of years of stellar fusion slowly radiating away into space. A white dwarf will cool for billions, eventually trillions of years, so slowly that no white dwarf in the observable universe has yet had time to cool completely. Every white dwarf that has ever formed is still warm. Eventually, in an almost incomprehensibly distant future, a white dwarf will cool to the point where it no longer emits visible light. It will become a black dwarf, a cold, dark, invisible remnant of what was once a star. No black dwarfs exist yet. The universe is not old enough, not by a very, very long way. The white dwarfs in the sky right now are all still warm, still glowing faintly, still radiating the last of their ancient heat into the cold dark of space. Patient, quiet, fading slowly over timescales that make human history feel like a single heartbeat. Part 5. The Supernova. Not all stars die quietly. Stars that are significantly more massive than our Sun, 8 times the mass or more, do not have the option of a gentle exit. When the fuel in their cores runs low, the consequences are catastrophic. As the core of a massive star exhausts its hydrogen, it begins fusing helium. When the helium runs low, it fuses carbon, then oxygen, then silicon. Each stage produces less energy and lasts for a shorter time. The final stage, silicon fusion, lasts approximately 1 week. At the end of that week, the core is made of iron, and iron cannot be fused to produce energy. Iron absorbs energy rather than releasing it. And so, for the first time in the star's life, the outward pressure of fusion can no longer support the weight of the star above it. In less than a second, the core collapses. What happens next is one of the most violent events in the universe. The core collapses so rapidly that the outer layers of the star, still falling inward, slam into the newly compressed core and bounce. A shockwave of almost unimaginable energy blasts outward through the star. The entire outer structure of the star, layers that took millions of years to build, is expelled in an explosion that briefly releases more energy than the Sun will emit in its entire 10 billion year lifetime. This is a supernova. For days or weeks, a single exploding star can outshine an entire galaxy of hundreds of billions of stars. In 1054, astronomers in China and the Arab world recorded a new star appearing in the sky, one bright enough to be visible in daylight for 23 days. What they witnessed was a supernova approximately 6,500 light-years away. The expanding shell of gas from that explosion is still visible today through telescopes. We call it the Crab Nebula. The explosion they recorded happened 6,500 years before they saw it. The light was simply arriving. Part 6. What the explosion leaves behind. A supernova does not leave nothing. At the center of the explosion, the collapsed core remains. What it becomes depends on how massive the original star was. For stars of moderate mass, the core becomes a neutron star. A neutron star is perhaps the most extreme object in the universe that we can still technically call matter. It contains roughly 1 to 2 times the mass of the Sun, compressed into a sphere roughly 20 kilometers across, about the size of a city. The density is extraordinary beyond any ordinary comparison. A single teaspoon of neutron star material would weigh roughly 4 billion tons on Earth. The gravity at its surface is 200 billion times stronger than the gravity you are experiencing right now. Neutron stars spin fast, extraordinarily fast. When a massive stellar core collapses, it conserves its angular momentum, just as a spinning ice skater pulls in their arms and spins faster. A core that rotated slowly as part of a giant star becomes, upon collapse, a neutron star spinning hundreds of times per second. Some neutron stars emit beams of radio waves from their magnetic poles, sweeping through space like cosmic lighthouses. When those beams happen to point toward Earth, we detect them as regular pulses of radio energy. We call these objects pulsars. The first pulsar was discovered in 1967 by astronomer Jocelyn Bell Burnell. The signal was so regular, so precisely timed, that it was briefly labeled LGM1, Little Green Men, because nothing natural, they thought, could produce such a perfect rhythm? It was a neutron star, spinning 30 times per second, sending out a beam of radio energy with the regularity of the most precise clock ever built. Part 7. The most extreme ending. For the most massive stars, those many times heavier than our Sun, even a neutron star is not the final answer. When a sufficiently massive core collapses, nothing can stop it, not even the quantum mechanical forces that hold neutron stars together. The collapse continues inward, past the neutron star stage, into something that has no physical surface, no definable structure in ordinary terms. A black hole. The entire mass of a star compressed into a single point of infinite density, a singularity, wrapped in a boundary called the event horizon, beyond which nothing, not light, not information, not time as we understand it, can escape. A stellar mass black hole, the kind formed from a collapsing star, is typically only a few kilometers across in terms of its event horizon, far smaller than a neutron star, yet it contains more mass, more gravity, and represents a complete break with the physics we use to describe everyday reality. Near a black hole, time slows, space curves. The laws of physics as we know them reach their limit, and beyond the event horizon, we simply do not know what happens. Our mathematics breaks down. Our models give no reliable answers. It is one of the few places in the universe where honest scientists say, we don't know. And there's something profound about that, a universe that contains objects so extreme that they exceed our ability to fully describe them, that push our understanding to its absolute edge, and then beyond. Closing. The cycle of everything. Every atom of carbon in your body was forged in the core of a star during helium fusion. Every atom of oxygen was created in a more massive star during later fusion stages. The iron in your blood was produced in the final seconds before a supernova, in that last brief week of silicon fusion, just before a stellar core collapsed. You are not just made of stardust, you are made of the specific products of stellar death. The supernovae that created the material in your body happened billions of years ago. Those explosions scattered their contents across space. Over millions of years, that material drifted and cooled and clumped together under gravity, eventually forming the molecular cloud that would become our solar system. The same explosion that ended one star began the process that would eventually produce the sun, the earth, and everything on it. Death and beginning are not opposites in the universe. They are the same process seen from different points in time. Right now, somewhere in the Milky Way, a massive star is in the final stages of its life. Perhaps in the last 1,000,000 years, perhaps in the last 1,000, burning through its final fuel, building iron in its core, unaware, if stars could be aware of anything, that the end is approaching. And when it goes, it will be violent and brief and extraordinarily bright, and the material it expels will drift through space for millions of years, until gravity finds it again. And somewhere, in some distant future, that material may become part of something, a planet, an ocean, a living thing that looks up at the night sky and wonders where it came from. The universe does not waste anything. It transforms. It cycles. It takes the end of one thing and quietly, patiently, over incomprehensible timescales, makes it into something new. You are are the proof of that. So tonight, let the stars burn at whatever stage they are in. Let the red giants expand slowly in the dark. Let the white dwarfs cool over trillions of years. Let the neutron stars spin their perfect rhythms into empty space. None of it needs your attention right now. The universe has been doing this for 13.8 billion years. It does not need your help tonight. Rest. You are made of everything that came before, and that is enough. Good night.